Okay, so hello everybody.
Hello.
We're starting the fourth lectures, numbers and names, and today we'll talk about the laws, or in mathematics they are called
Theorems.
no, laws are called axioms.
Axioms. You told me about them.
Axioms. Okay, uh, you know where laws come from in society, right?
Yeah.
Parliaments, right, and everything, all these procedures, everything, right? In physics, it comes from experience. So we do something, then we find something, what the result of it, and then we think about it, and then we may think about something that which is called the law. And in mathematics, these laws are called axioms. Where do they come from? That's an interesting question. Some people think that axioms are were invented by some genius mathematicians. Somebody thinks something else. So this is one of the questions that I want you to think of, right? So where the axioms of mathematics, which we are going to talk now, where are they come from? Where do they come from? So, but anyway, there were once upon a time there lived in ancient times there lived a Greek philosopher whose name was Euclid.
A what?
Euclid. Euclid of Alexandria, which means that he lived in the city of Alexandria, right? So Euclid. He lived about 300 years before Christ. And he come to us with something that we call axioms of geometry. So, axiom geometry. Geometry.
Wow. Geometry.
Yeah. Geometry is. You have a question or?
No, I'm just saying lots of geometry.
No, okay.
Haven't you tell me about Euclidean geometry?
Yes, it's Euclidean geometry. Yes, agree. Yes, Euclidean geometry is exactly what we're talking about. Axioms of Euclidean geometry were suggested by Euclid, right? Okay, and axioms were about something that actually geometry is talking about. And geometry is talking about certain things. The first thing which is geometry is talking about, so geometry and geometry objects. Geometry objects, we have one simple object we call point. Point.
And
So something very small that have no size, like a piece of sand, but without size.
Papa told us it's a paradox. How can we learn about how lines in geometry? How can we write something?
Okay, guys, not too fast. Okay, we'll talk. Okay, the point, right? Then the other thing, the other object of geometry is called straight line, or we'll call it just line, but you know that it's straight, right?
Infinitely.
Straight line. And this is something like this, right?
If a line isn't straight, it's not a line. Lines have to be straight.
Yes, agree. But anyway, so sometimes they call line not straight things. But anyway, so we know that line is straight, right? What is straight, by the way, it's a big question. But anyway, we can imagine something that goes like this, right? And it goes both sides. It goes to infinite distance, right? To the right and to the left, whatever, right? And then what do we have else? So we have something actually what is actually called plane. Plane.
Papa told me about planes.
Plane.
Oh, yeah,
Plane is just straight surface, right? Something like this, like a table, but you know, stretched to infinity, to all sizes, right? So something like this. So plane is something like this, right? Stretched to infinite distance everywhere, right? But it's flat. It should be flat, straight. So each line which belongs to the plane, right? It is straight line. So we have this. lines like this going in place. So we have that kind of things, right, in geometry. And now what Euclides said. One thing he said that was called axiom, right? If we have point and we have line, right? So one point can lie on infinite number of, one point can lie on infinite number of lines, right?
Yeah, we know that.
It means they're intersecting in this point, right? Infinite number, lots of, right?
Yeah, what counts that?
Mm-hmm. The other, this is maybe axiom, I don't know which exact number was it. Let's be axiom number 1. I'm not sure was it first in Euclidean system, but we may tell it's axiom number 1. Then the second axiom is if we have two distinct points, so points that are not coincide to each other, not one point but 2 points, right?
How many lines?
And those 2 points, they lie on just one single line.
Dita!
Oh.
We learned this in geometry with Papa.
Okay, good. We just repeat these things, okay? A little. So this is number 2, right?
Uh-huh.
And now what we can tell? If we have 3 points, again distinct 3 points.
It depends where they are. Yeah, it depends on where they are. Like we said. But
Guys, don't go too fast. Okay? If we have 3 points, right? Of course, when we take 2 each, to which we can pass through them. Okay, we can say pass through, right?
Yeah.
3 lines, right? Through these 2, this line, through these 2, these 2, and through these 2, these 2. And again, those lines are just single because if you have 2 points, they can lie only on one line, not anymore, not other lines. And the axiom number 3 says that if you have 3 points, whatever lines are, 3 points, they can lie on only one plane.
Okay.
So if you have 3 points,
Yeah.
and they lie on the plane, there's no other plane can go through these 3 points. It's still the same single plane. This we call the axiom number 3. Okay?
Okay.
There's also axiom number 4, which we may mention here, which is important too. If you have one line passing through 2 points, right? For example, and we have some third point, right? And this point lie on the plane, we can pass only one single line which is parallel to that original line. Parallel means that they do not intersect. But they
Lines that we know.
Yeah. Huh?
Yeah, Dida.
Mhm.
Parallel lines are lines that are beside each other that can go on for infinity without touching each other.
Yes, without teaching each other. But it's important to say that those lines should be on one plane. So so this line should be on this plane. So we are talking only about lines that belongs to the plane. So all these points on this line this goes on this plane. Okay. So this seems like maybe pretty obvious in many ways, right? Also, I'm not sure that it was called axioms by Euclid, but there was, or maybe it is theorems, but it is said that the line can many points can be on one line. Many points, not only 2, but many points. In this way, yes, in this way you can say that the line consists of these points. So like many points, right? If they lay on one line,
Yeah,
right?
because there's always room. Because
Okay.
these lines go on for infinity?
They actually form this, yes, yes. So the infinite amount of points. So the first question is where these axioms actually came from. That's one thing that I'm asking, that you would think with you and Papa. Where do they really come from, these axioms? The second thing, which is maybe the question, but we talk about this, what it has to do with reality. Okay, we're talking about geometry, right? And geometry is actually about something like measuring distances, right? Looking how straight are the lines of like buildings or like our fields or roads. So very, 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 very practical, right? But interesting enough, we spoke about this, that in reality there are no straight lines. So because each line is actually fractal, remember? So
Yeah, what? Fracture.
fractal.
Oh.
Fractal. So
But like little cracks and bumps in them.
so there are no straight lines.
Points in it, and they're empty. You can never ever fill a point completely. It's not talking about it's talking about this flat straight line. I know.
Okay, good. So so straight line is so-called idealization, right? Something like that. Again, that's the question: where did it come from? Did Euclid imagine it or invented it, or is there something? But it has something to do with reality. We have something that looks like, at least like straight line, right? For example, like if we get a laser, right, and laser delivers us a stream of light, all right, the flash of light, right? This light, like it looks like very straight, right, and it can go to miles and miles ahead, hundreds of miles.
Yeah, you told me this, data. Yeah.
They use, that scientists used laser beam, use it to measure distance to the moon. They put reflector on the moon, and they send their beam and get the reflection. So and it's pretty big distance.
Did they also use a laser to measure the length of a meter?
Yeah. Okay, so we have something that looks like straight line, but it's not straight line. But anyway, and we have something like point, but again, a point is very much idealization, because there's no points in reality. Like the smallest thing that we actually have are elementary particles, or quanta. Yeah. Remember this, quanta, right? Quanta. And these quanta are not of zero size. They're not infinitely small. They actually have certain size, which can be measured. It's measured. It's very, very elusive, but still it can be measured in some way. So there are no points, no lines, but anyway, we have some geometry, right? We have some axioms. The other thing interesting about axioms, which was actually found out much later, not in 300 BC, not by Euclid and not by other guys, but actually it was found in already 20th century by different people. One of them was pretty famous mathematician Hamilton, and they noticed interesting thing, that when we're talking about when we're talking about axioms, right? We're using certain words like point, right?
Yeah.
But we don't know exactly what point is. It does not exist in reality. Maybe it's some idealization, but we don't know exactly what point is. Then we use another word which is called line, right?
Yep.
Again, we think that line may be something like this, but we are not sure, right? So maybe line is something else, or maybe some other thing, right? And now we're using some other words, which is like lies on, right? Point lies on line, or line passes through, right? Passes through points, right? So point lies on line, and line passes through point. right?
Yeah.
And then we use some other things which are called numbers. 1 point, 2 points, 3 points, so they're countable, right? We can count points. And also lines, they're countable too. There are 1, 2, 3 lines, or maybe infinite lines, but anyway, we can count. So what we have like as a result of all this? That we're using some words like point lies on, like for example, point lies on like line, right? But we don't know nothing about what is point, nothing about what means lies on, and nothing about line. So what Hamilton suggested, he said, okay, we cannot say like exactly what is this. Let's maybe talk how it was put formally. We have 3 words like point, line, and lies on. Okay? And we can, because they're just words, right? We can rename them, right? We can name this word like A. We can name lies on like B. And we can rename line like C. Can we do it?
Yeah.
They're just words, right? So why not? We can rename them, just give the other names.
It's better to keep them the way they are.
And this maybe, but it's not mathematics. Mathematics doesn't choose easy ways, you know, they choose interesting ways.
I have a question.
Yeah, sure.
Did you name a point A, point B, and a line C?
No. I mean the word point or the term, as we say, like term.
Aren't you listening?
This term we rename as A.
Oh.
And another term lies on, we renamed as B. And another one more term as line, we renamed as C. Right? So the sentence or the phrase that point lies on line, we'll write like ABC. Right?
Uh-huh.
And all of the rest thing like passes through, we can rename as D, right? So if we want to say that line C passes through point A, we will write what? Line C passes C, D, and what? A. So line passes through point. And which point? We can rename also one point. We can rename some else like A1 or 2, right? We can say that like line C passes through A1, the same line C, like for example C1, right? Again passes through another point A2. Can we do that?
Yeah.
So it means that this line passes through 2 points, A1 and A2. And actually, if we think about it, right, we can talk about many things in geometry. We write them like this, right? And now there's a question. So this thing then, what Hamilton suggested, that what we see in our mind, like what we think, and what Euclid suggested, that point is something like this real point, right, somewhere, and line is some line, like beam, whatever, right? And lies on means that point lies on this line. He suggests that actually it can mean whatever thing, whatever you can imagine. But
donuts and hot dogs seems good. Anything could mean computers or
yeah, whatever. He said that because we don't know anyway what point is, we don't know exactly what line is, we don't know what exactly means this, lies on or passes through. He suggested, okay, why not? Let's just talk about it. We have something, whatever it is, but this whatever it is, this A, C, B, and D, right? They still obey the axioms that are actually suggested by Euclid. And these things can be written like this, like sort of sentences, right? There's axioms like laws. They can be written like this: C1 D1, C2 D2, and whatever. I won't do that because it's a little, a little too messy. But you can understand it, that we can write it like this by renaming and writing something.
Yeah, but then we don't do that because then other people will interpret it as something else. Cause nobody really knows what ABC means.
Yes, but remember, mathematics is about, remember these variables, there are numbers, 1, 2, whatever, and also variables like x, right? Which can be 1 or 2 or whatever.
Yeah, but as you see, no. It can be all the numbers. Yeah, but what about n? N is all the numbers. N is only natural numbers, I'm pretty sure.
Yes, okay, it can be, yes, but like in algebra, right? We usually mean by x some number, right? It can be integer number or maybe a rational number, whatever, right? But anyway, they're numbers, right? But here under A, B, and C, again, we suggest something that can be whatever, anything at all, anything at all. Not only numbers, but anything. So it's anything at all, but so we still have some axioms. So we have some number of phrases, right, which are saying that with this number of phrases, we have something to say about these A, C, B, and D. We don't know what A, B, C, and D are, but we can tell something about what they do. In abstract way. This is called this idea is called formalism or formal approach. Form. So we have certain form, but we don't know what is inside form is. That's called formalization or formalism. So, wow, that is. There's a. No, that is crying there. What? Yeah, that's a real. Something happened. Okay. And that's our guy just said. Nati's crying there. Okay. So again. So we have some formal things, some number of phrases. We can tell that they are phrases of certain language. Phrases, right? Which we call axioms. But what their phrases are about, what's the meaning of this, we don't know. We know only these phrases by themselves. If we want to know something like more materials, so we would think about what these C, D, A actually mean. So we can talk and think about, like, there are some points, real points, like in our space-time, right? Like some lines, like beams of laser light, something like this. And when we think something that actually can be that we mean something under A, C, and B, we call this interpretation. Oh, make it here. Interpretation of the formalism. So we have formal phrases, which are axioms, and we have interpretation. In Euclid geometry, interpretation is like our points and beams and lines in our space, right? Or maybe space-time, whatever. Okay. I want you to think about this idea because it's a very important thing in mathematics. And with this comes another question. Can you think? You talk to Papa and just discuss this. Can you think about some other interpretation other than real point in space, real lines in space, and still obeying these sentences of axioms? You may write axioms like in this way, step by step, like that. Like 2 points, like for this is like through points, just one line can go, like C1 can go through different points N1 and A2, right? But we cannot. But if we write here like C2, dA2, right? And C2 dA1, this would be wrong axioms. And they cannot be in this set of the axioms. Just think about it. So this goes only with one line and 2 points. And again, not 3 points. Well, the 3 points you may think about it, but you may talk between you others. So what I want you to think of, right? To really think of. Can you imagine something that are based, at least, maybe not all, but some of these axioms, right? But they are not really the points and lines. Something else.
Like
around you.
It could be Z.
No.
It's not that easy. But it's not easy. It's a pretty, but I think it's interesting thing to do.
No. What Jed is asking is, you have this formula ABC, and in our interpretation, ABC means A point, B lies on, C line. So point lies on line, right? What other interpretations for the variables A, B, and C can you have so that the sentence ABC is correct? Not A1, B1. Like, replace A, which is a point, with something else. Replace the meaning behind the word A with something else.
Like donuts.
Like donuts. Yeah, why not? Let's A be donut, right?
Donuts on trays.
Oh, that's a good one. Yeah, on trays. Yeah.
Donuts on trays.
Donut, then what?
So,
Lies on.
Lies on? Maybe not lies on. Let's maybe consists of.
No, we're gonna say donuts lie on trays.
so
No, lies on. I don't want to use lies on. Something else.
Okay, not lies on.
donuts taste
Donuts, taste, delicious. So this is ABC, right? ABC. Now,
Okay.
if we take this, right, we should check how the axioms are. The axioms correct in this thing? Like, for example, this C is, what is C on us? C, we have delicious.
We have D. We don't have D.
Yeah.
Ah, we don't have D yet, right? But yeah, okay. So you should think about it, what it means. Guys, but okay, guys, this is question for you. You understand the idea, right?
Yeah.
So this is question that you work by yourself, and you think and talk to Papa, and you come with questions if you want, if you still have questions. But I think you'll understand how to do these things. Okay, you got the idea, right? So we continue just a little.
Please pass the tray. I got it. Please pass the tray.
Okay, this is Law's axioms. Okay, so you got the questions, right?
Yeah.
And
So wait, the cookies.
okay, and now just a little more on this, because we're talking about geometry, right? And geometry has very interesting expansion, or how you call it. It is called analytical geometry.
No, what?
Analytical geometry. Analytical geometry is geometry, but with numbers, not with lines, like you write, like triangle, right? Like this, right? You draw the lines, you draw points and everything like this, right? But analytical geometry is about numbers. So analytical geometry starts from the line, right? Straight line, and it transforms it into
Number line.
yes. So 0, 1, -1, right? 2, whatever. And we usually put an arrow here, right? This positive direction, right? This is negative direction. And this is 0 point, right? So And analytical geometry, it not doesn't stop at one number line, right? Usually it talks about many number lines, and they are called dimensions. Remember?
Oh yeah.
So one number line is there, it goes like one dimension, right? Another, you know this word perpendicular, right?
Yeah.
You know, right? So it's perpendicular to x, right?
X.
This is called y, and like z, and also it can be more, like for example, we don't take it right more, but right now like it's a corner of the room, right? For example, right? This is x-axis, this is z-axis, this is y-axis, right?
Yeah.
And these angles are straight. All of these angles are straight between
Right angles.
zx, yx, zx. All of them are straight, right?
What?
Right angles. They're called right angles.
Right angles, yeah. Oh, I'm sorry, not straight. So, sorry. Right angles, yes, right angles.
Oh wait. Yeah. Is
Mhm.
it
Yeah, they're right angles. Yeah.
ZY?
Yeah.
No.
Yes, yes it is.
Oh wait. Oh no. Yes it is. Yes it is. It is. I don't see that. Yeah, it's a right angle.
Actually, they're talking that the axis z is perpendicular with the whole plane, x and y.
Step. They're not looking
This
at
is the
that.
plane
See?
where this axis lie, this plane, and z is perpendicular to the whole plane, so to the floor, right? This is floor. Floor is a plane where x and y lays,
I see what you mean, Katya. Right.
and z is perpendicular to the whole plane.
So
The
you
same
see-
thing with y. This x is perpendicular to this wall, z and x wall, right? And x is perpendicular, the same thing to that wall, to zy wall. There are three walls in the corner, right? And floor. Two walls and the floor, right?
Yeah.
So, and these things, they form what we call dimensions. We have dimensions in our space. We have three dimensions, right? And the numbers, like each point in these three dimensions has certain coordinates. Coordinate means something like this. So if we have one point, right? One point. We do something that is called projection. We put the line perpendicular to the axis, to the plane x and y. Go like there until it intersects the plane.
Uh-huh.
Some point C, right? Like this. And then we draw another lines parallel to y and parallel to x, to here. This and this. Okay? And also we draw the line perpendicular to this z, right? So in these distances with this along this axis, right? They are called coordinates. So this is x coordinate, x. This is y coordinate. This is y. And because it's number, it's point A, right? So point A has that coordinates x, y. When we call it x1, I1, y1, and z1. Z or z, x1, c.
Why not?
Okay. So these are called coordinates of this point, right? It's all about perpendiculars or right angles. Right angles. All these angles are right. This angle right. These angles are right. This angle right. This angle right. This angle is right. You see? So that's how you think about coordinates, right?
Mm-hmm.
Also, what we can say about dimensions, there's an interesting thing which is called metric. Metric.
Oh, but the metric system.
Metric system, yeah, metric is a measure. So metric means that you measure the distance with the some metric, right? With the some measurement, some some tool of measurement. Like what you usually use for measure distance. What is called?
Kilometers.
A ruler, ruler. In the simple plane, it's just the ruler, right? So
Yeah.
so you use the tool which is called ruler, right? So, but how in this analytical geometry, how you actually measure? You have coordinates. How you measure the real distance? Like this is point 0. Usually they name it like O or just 0. This point 0, and the distance between 0 and A is this line, right?
Yeah.
This line. Remember, it is 3 dimensions, so it goes from the corner and somewhere in the space, right? Somewhere from the corner. How you measure this thing? Like if you in the plane, okay, you have like, for example, y and x, right? Triangle, right? And you want to, okay, better like this. X and y, and you have certain point A, right? For example, coordinates are this, so this is like x1 and this is y1, right?
Yeah.
So a distance which we measure is this, right? So if you remember, this is right angle, this is right angle too, but this is not, we're interested in this one. So you see, this is coordinate x1. This distance is, what distance is it?
X1.
No, x1 is this. What is this?
A1? Oh, no. Wait, no. Isn't that YA?
y1. This one.
Oh, Y1!
Yeah. So this is the same as this. It's easy to see, right?
Yeah, sorry, I'm blind.
Yes. And because this is right triangle, right? You know this theorem. This thing is what?
The
How this thing is called in
hypotenuse.
hypotenuse, right? And this hypotenuse, like let's name it like S, right? The length S.
Huh?
What can you say about the length of this hypotenuse?
Well, what you could do, you can do what was it? Y1 squared
Так.
plus Y1 squared times plus X1 squared equals S squared.
Exactly. This is theorem of
Pythagorean theorem.
Pythagorean
Oh
theorem.
Pythagorean, right? Pythagorean theorem, right? So we have S squared equal this and this and this, right? So look now let's look at this three-dimensional thing. Let's look at this three-dimensional thing.
Oh my God, it's the same thing. Yeah.
Well, there's 3 numbers though. That's the difference.
Not yet. So we can first think about this projection of this OA here. Like if you project the whole line OA to here, it will be OC, right? So OA is like projected to this plane, projected to the OC. So this length, it's y and x, right? This S is what? If you look to this picture, this S squared is what? Is x1 squared plus
Y1 squared.
y1 squared. So we know at least this. We will call it SXY, for example, because it's S on the plane X and Y, right? So we know that SXY squared equals x1 squared y1 squared, right? So we know this now. And what is this? Can you tell what this distance is? What is this?
A plus C. Wait, no. A plus C. Did that A plus C?
No.
8 times C?
No.
Guessing.
Don't guess.
Think.
Wait. I am.
Look at the projections.
This
Z1.
Z1, right. So we can say that S, this S, right?
Z. Where's Z?
The projection. See the projection right there.
Oh.
Here,
Yeah.
here, here. So this is Z1, right? This is Z1.
Huh?
So this is Z1 either. It's the same here and here. So if you look at this, right, you can write about this, that this equals x1 1 squared, right? So we know this, and we know this because this is Z1, right? And this is again right triangle, because this thing is a projection perpendicular to the whole plane.
That's
So
the
this
same
is-
thing up there.
Yep.
And now S squared
What?
plus
X1
is
squared.
Z1 squared, right? Plus,
Oh, 1 squared.
plus, what, this squared, right?
That's, what is that?
SXY squared.
Y squared. SX.
And SXY we know, it's this one, right? And we can write the result that in 3 dimensions, S squared, oh sorry, oh, we won't write that, it's simply that. We remove the indexes, so we have that S squared in 3 dimensions, X squared, Y squared, and that Z squared.
Because there's three dimensions.
Uh-huh.
Those are
Now, can you make a guess? Like if you have 4 dimensions, what would it be? Like the fourth is T, like T.
S squared equals X squared.
S squared.
S squared equals X squared plus Y squared plus Z squared plus T squared.
Plus T squared. So for 4 dimensions, it will be yes, X squared, Y squared, or Y, right? Y squared, Z squared, plus T squared. And the same thing for if you have n dimensions, the same thing. So this is the theorem, Pythagorean theorem for many dimensional world. Whatever dimensions you have, it's still there. So it's a very important thing to understand in geometry. And interesting enough, baby, just to mention that actually it is correct in the so-called Euclidean space, right? But like for other spaces like space-time, like for example for space-time, it's not correct, but very close to that. It's space-time is 4-dimensional thing, but here is not plus but minus.
She's minus.
Yeah. Minus. And this is called pseudo-Euclidean, pseudo-Euclidean, or simply Einstein spacetime, or more correct, it's Minkowski spacetime, because Minkowski was the guy who first suggested this analytical geometry for spacetime. Minkowski is like Minkowski, like this, something like this. Okay, it's just for you. And okay, and that's it. I gave the questions, right? So any questions from you guys? No.
No, I have a question.
Okay.
What if, can you go any dimensions plus? I mean further than space-time dimension.
Of course, you can have whatever dimensions you want. Still, for Euclidean spaces, you still have plus that squared plus whatever you have number of dimensions. You have number of these things.
I did.
Mm-hmm.
No, Babu. Oh yeah, Babu. Yeah, can you get Babu over here, please?
Okay, Jess, I'll finish recording. Okay, so no questions anymore.
No.
Don't forget to answer my questions. Okay. See you there.